Hello, statistics students. My name is Jamie Amy, and we are starting Chapter 2, Exploring Data with Tables and Graphs. Section 2.1 is on the frequency distributions for organizing and data. Here we have a set of data. It's the IQ scores for a low-lead group of 78 people, and you can see a list of all 78 IQ scores here. But it's difficult to pick up on trends or groups of IQ scores when you see it in a list like this. So it's often beneficial to organize this into a table or a graph. One example would be right here. It's called a frequency distribution table. It's separated into 5 classes. One is right here, second, third, fourth, and here's the 5th class. To make it into the 5th class, you would need an IQ score of 130 to 149. And if you look through our data, there was only one person who had an IQ score of between 130 and 149 inclusive. And it looks like that person is right here, the IQ score of 141. That's where the 1 came from. IQ scores between 90 and 109, including 90 and 109, if you went through and counted them, looked very carefully and counted them all up, how many would you get? Answer, 35. That's where the 35 came from. A lower class limit is the smallest number in each class. So we have 5 classes, which means we have 5 lower class limits. They're right here. 50, 70, 90, 110, and 130. There's the list for you. An upper class limit is the largest number in each class. So here we have 5 classes, so we should have 5 upper class limits. Ours are 69, 89, 109, 129, and 149. There's the list of upper class limits. Class boundaries are the numbers used to separate classes. Okay, pay attention. So far we had 5 lower class limits, 5 upper class limits, but for class boundaries, we're actually going to have 6 of them. Let me show you how to find them. 4 of them are pretty straightforward. The IQ score separating 69 and then 70 to get into this class would be an IQ score of 69.5. So that is one of our class boundaries. 89 to 90, the IQ score separating those 2 classes would be 89.5. So that's our second class boundary, or another class boundary. 109 to 110 is separated by the value 109.5. So that's another class boundary. 129 to 130 is separated by 129.5. So that's another class boundary. Okay, so there are 4 of them, all right? But remember, we're going to have 6 of them. Here's the list of all 6. These are the 4 we've already accounted for. So let me show you where this smallest class boundary and this largest class boundary came from. If you were to pretend that there was another class of IQ scores above this, it would end at an IQ score of 49. So the IQ score separating this invisible class, if you will, would be the number separating 49 to 50, which is 49.5, and that is where that lowest class boundary of 49.5 comes from. Then the last one, the 149, comes from the upper end of the table. If there was another class of higher IQ scores, it would be 150, starting the next class out. 149 and 150 are separated by the number 149.5. So that is where the 6th class boundary comes from. So 5 lower class limits, 5 upper class limits, but 6 class boundaries if you have a frequency distribution table with 5 classes like we do here. Class midpoints, that's the average between the lower class and the upper class limit. Let me just pick one to show you as an example. This class right here, lower limit is 90, upper limit is 109. Definition said it's the average between the lower and the upper class limits. So if you were given these two numbers, to find the average of two numbers, you would add them up and divide by 2. So the class midpoint for this particular class would be right here, 99.5. That's the middle one. That's this one. So I want you guys to look at how we got 59.5, 79.5, 119.5, and the last class midpoint is 139.5. And you calculate those by doing the same thing we did for this class, the third class example. Add them up, add the limits up, and divide by 2. And this one right here is, please stop that, is how we got the 99.5. So try the other 4 classes. So take your calculator out, add the limits together, and divide by 2 to make sure you know where all 5 of those class midpoints or how they were calculated. Last term here is the class width, the difference between 2 consecutive lower class limits. So again, let me choose an example here. Consecutive lower class limits. That means 2 lower class limits in a row. So I'll just pick these 2, 50 and 70. Those are consecutive because they're right in a row, and they're both lower class limits. Well, the difference between 50 and 70 is 70 minus 50, which equals 20. So all 5 of our classes need to have the same width. They all need to be 20. So it doesn't matter which 2 you choose. 130 minus 110, you'll get 20. 110 minus 90, you'll get 20. And that is a requirement because when we turn this graph into a histogram, we want the bars to have the same width. So this here is a class width of 20. Okay, don't put this slide away completely. We're going to use this to show how to go from this graph, this table right here, which is called a frequency distribution table, to our next table right here, which is called a cumulative frequency distribution table. So these numbers here come from, refer to the last slide. There were 2 IQ scores between 50 and 69. Next, if you recall, look at the last slide if you need to, there were 33 IQ scores in this class. But why is there 35 here? The reason is because we're accumulating the frequencies from above. That basically means add the number above it. So we have 33 plus 2, that's where the 35 came from. Our third class, look back at your last slide. There were 35 IQ scores in the third class. So what we do in this table is add the frequency from above. So 35 plus 35, that is where we got the 70 from. Let's go again. If you look at the last table, we had 7 IQ scores in this class. Accumulating, okay, so adding the 70 from right here, that is how we have 77 IQ scores. And notice that those 77 IQ scores, we had to change we didn't write the lower class and upper class limit. We had to state that we have 77 IQ scores that were less than 130. So make sure you're adjusting your first column correctly and your second when you are creating a cumulative frequency distribution table. Last one, we had an IQ score, one of them, that fell into the highest class. So we added that to the 77 before, and that is how we came up with our 78 IQ scores of less than 150. All right, now, you may want to know the frequency of each class. You may be interested in the cumulative frequency of each class, but sometimes we're interested in not just the count, but the percentage. So here we have what is called a relative frequency distribution table. And relative frequency, you want to think percentages. If you're asked to construct a relative frequency distribution table, then you want to provide the person that will be looking at your table with the percentages of IQ scores that fell in each class. So for this first class here, if you guys recall, you can look back at the last slide, we had 2 IQ scores in the first class. How does that turn into a 2.6? Well, we divide it by the total number of IQ scores, which was 78, and that's going to give us a decimal. It's going to be 0.26 something. Oh, I'm sorry, it's going to be 0.02 and so on. We move the decimal 2 places to get our relative frequency of 2.6%. All right, I want you guys to get your calculators out and try that with the next 4 classes, okay? Calculators out. Okay, for this one, we've got to type in the 33 that we had in that class of IQ scores. We're dividing it by 78. Look at the decimal that you have on your calculator. Move that decimal 2 places to the right, or you can hit multiplied by 100. We learned in the last chapter that does the same thing. And you should see where this 42.3% came from. All right, I want you to pause the video and try that with the next 3 to make sure you know how to calculate the 44.9, the 9, and the 1.3%. Welcome back. Hopefully you did all right calculating the percentages for a relative frequency distribution table. Okay, a table is nice, but sometimes, depending on your audience, you want to present your data with a graph. So this right here is called a frequency histogram. It's representing the same data, you guys. These are still the same 78 IQ scores. We went from a list to a table, and now we're seeing them here in a graph. The higher the bar, the more data values fell in that class, or we call that the higher frequency. So that first class, if you recall, it only had 2. That's why that bar is kind of short. And then it jumped up. We had a lot of people, 33, or you can think of it as 42.3% of people that fell in this class. So there's the width of the class, and the height is the frequency. Our third class had the highest frequency. That's why it's the highest bar. There were 35. Same width, higher frequency. Our fourth class had 7 people with IQ scores in that class range. Same width, the frequency is 7. And our shortest one had the lowest frequency of 1. On the horizontal axis, this particular frequency histogram was constructed with these numbers. These numbers should look familiar to you. You wrote them down. Just one slide back. There are 6 of them. So I want you to look one slide back and tell me what these 6 numbers are called. If you said the class boundaries, you got it right. Good job. You don't have to construct it with the class boundaries. You could also construct it with the class midpoints. And those 5 values would go here, 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 label it right here, and you would label it right here if you wanted to present your histogram with the class midpoints on the horizontal axis instead of the class boundaries. Either way, no matter which way you decide to present your data, you need to make sure it's accurate. Presenting it one way should not make it appear different than presenting it using a different, say, class boundaries versus class midpoints. All right. Section 2.2, we dive a little bit more into histograms. They're a visual tool. They're used to analyze the shape or the distribution of the data. So here we have even more classes. So breaking this down, this is the arm circumference in centimeters, and remember the height is the frequency. Notice here, just want to point out that they put some class midpoints on the horizontal axis to show their data. It looks like a very nice graph. And what we want to point out about the graph you see here is that the shape of it, so not each individual bar, but rather if you had to put one shape to describe it, this takes on what we call a bell-shaped curve. This is something we study a lot in statistics, where the left half is roughly the same as the right half. It's symmetric. They increase, then decrease. We call that normal distribution of data. That is the shape. All right, you guys, these need to go hand in hand. Bell-shaped normal distribution, okay? Bell-shaped normal distribution. Remember that. All right, some of those features that I was rambling about are written here for us more nicely. The frequencies increase to a maximum and then decrease. That is one characteristic of the normal distribution or bell-shaped curve. The graph has symmetry. The left half is roughly a mirror image of the right half. Another characteristic of the bell-shaped curve. We're moving on to examples of normally distributed data that fit into the bell-shaped curve. One would be the heights of adult males. So males, if this was a histogram representing your heights, majority of you would be toward the middle. Like we'll learn measures of center. This would say the average height of a male. That's where you would find the highest bars because it's where most men would lie, their heights. As you get taller and taller, there are less of you, right? So maybe like some NBA basketball stars, they're up here, so it gets less and less. Or maybe in this direction, very, very short, there are less and less of those, okay? So we increase, majority of males' heights would fall in the center, and then we decrease. Same thing with the arm circumference here. You can see that majority of arm circumferences are in the center, increasing, decreasing. So less on the extremely large arm circumference and less of the more extremely small arm circumferences. Test scores given to a large class, sometimes called grading on a curve. That's another example. If you guys all took a test and I had a lot of test scores and I was asked to grade on a true curve, then the majority of people would receive the letter grade of C. There would be less people who receive the letter grade of a B and even less who receive an A. This group of people right here would receive a D, and a small group here would receive an F. That is what we call grading on a curve. It fits into that normally distributed bell-shaped curve. Last example, the blood pressures of pregnant women. Okay, if we measured the blood pressures of pregnant women, majority of them would lie in where the average is, okay? And then some of them would have higher blood pressure, a few would have very high blood pressure, some would have a little lower blood pressure, and a few would have very low blood pressure. Okay, so those are examples of data that takes on the shape of a bell, and we call it normal distribution. Now, the one in the middle here is most like what we just talked about, but let's talk about if the distribution is skewed. A distribution of data is skewed if it is not symmetric and extends more to one side than the other. Data skewed more to the right, we call positively skewed, so it has a longer right tail. Okay, I'm looking at the three. Which one has a longer right tail? Looks like this one. This is like the right tail right here. So I'm thinking this one is skewed to the right or positively skewed. Data that is skewed to the left we call negatively skewed and has a longer left tail. Okay, so that looks like this one, longer left tail here. This one would be considered normal, okay? It's symmetric about the center, tails are about the same. All right, so let's see if I got those right. Symmetric is the middle one. Skewed to the left, that was correct. That's negatively skewed. So what you need to do to identify that is find the longer tail. Whatever side it's on, that's the direction it's skewed, and that would be on the negative side of a number line if you had 0 in the middle, so we call it negatively skewed. And skewed to the right, again, the way you would want to identify that, find the longer tail. If it's on the right, we call it skewed to the right. And if we were looking at a number line, these would be the big, larger numbers, so we would call that positively skewed. Okay, so what does that mean statistics-wise when we're crunching numbers? Okay, we've got all this data. Well, when we find the mode, that's the most frequently represented data value, that's always going to be the tallest point. We know that because that's the highest bar. If you then calculate your median, that's where you line them all up in a row and you find the one in the middle of the row. If your median is to the left of your mode, and finally, another measure of center is called the mean. That's where you add up all the values and divide by the number you added up. If that is even further left of the median, that is when you have negative skewness or left skewed. Contrary to this side here, mode, highest point. If your median was to the right of that and your mean even further to the right of that, then we would see a positive skewness or right skewed. What about this one in the middle? Well, if it is perfectly symmetric, your mode would be right in the middle, your median would be right in the middle, and your mean would be right in the middle. All right, we do not have a bell-shaped curve here, so we would not call this one normally distributed. This looks like a rectangle, okay? Whenever we see a rectangle-shaped data, we call that uniform. That's where all outcomes are equally likely. Each variable has the same probability that it will be the outcome, okay? So you got to link these together, okay? Uniform distribution, rectangular shaped. Link them together. Uniform distribution, rectangular shaped. All right, so the stuff we looked at so far, like the pulse rates of pregnant women, that wouldn't take on this shape. That takes on the bell-shaped. So what would take on this rectangular shaped? A deck of cards has within it uniform distributions. All right, that means that the likelihood of drawing a heart, the likelihood of drawing a club, the likelihood of drawing a diamond, or the likelihood of drawing a spade, if you were pulling one card out of a fair deck of cards, those are all equally likely. So all of their bars would have the same height and it would take on a rectangular shape. That's what makes it uniform. Flipping a coin has a uniform distribution because the probability of getting either heads or tails in a coin toss is the same. So uniform distribution, we link with the rectangular shape. Normal distribution, we link with the bell shape. Last section in 2.3 is on graphs that enlighten and graphs that deceive. Here we have a dot plot. This is the pulse rates of males. Dot plots are very powerful. It's a graph in which each data value is plotted as a dot along a scale of values. Dots representing equal values or like a multiple, a repeated value, they get stacked higher and higher. So dot plots are nice because you can see the shape of your distribution, but at the same time, you could go in reverse, if you will, and you can find every single individual pulse rate of males from your study. For example, this dot let's go with an easy one, right here. That dot means that you had one male with a pulse rate of 50. This dot right here means that you had one male's pulse rate of, looks like 82, okay? We actually had 2, 3, 4, 5, 6, 7, 8 males with pulse rates of 82. Okay. The stem plot is very similar to the dot plot. In fact, if you could just take it and turn it 90 degrees upward, you would be able to see that the shape of it. So this one also has a bell-shaped curve somewhat. But the way that the individual data values are represented is slightly different. 4 would be the first number in the pulse rate. 0 would represent the last number in one male's pulse rate. So that's why we have a pulse rate of 40. And now you go again. You go back to the stem right here. So 4, and then you go to the 2. So another one of our males had a pulse rate of 42. So it's the same as up here on the dot plot. There's the 40, and there's the 42. It's just in a stem plot, we put the 4, then the 0, then the 2. And both of them, you can work backwards, if you will, and not only get the distribution or shape of the data, but then you can back up and still identify every individual pulse rate from your particular sample. Here's an example of a scatter plot. You'll need 2 variables for scatter plot. This one we have the circumference of the waist in centimeters, and we're plotting that compared to the circumference of the same person's arm in centimeters. So one dot right here, that's just one person's measurements, but we get 2 reads on it. We get their waist circumference and we get their arm circumference, their X value and their Y value. The reason for a scatter plot is oftentimes to check if our dots, although scattered, if they fit some kind of best fit line, because if they do, we can use the equation of that line to make predictions. Like, okay, well, we got all this data, but what if we happen to have a person with a waist circumference of 130? As statisticians, can you predict the arm circumference? And if your data does fit a best fit line like this, then you can use the equation of the line to make a prediction. You would go to the arm circumference corresponding to the waist circumference of 130, and that would be your predicted arm circumference. We get into scatter plots a lot more in Chapter 10. Multiple bar graphs comparing the male versus female median income by gender. So you can see over the years. This is often used to represent the difference. So we can see here that females' income was less than half. Here again in 1960s, less than half. So I'm just looking at the height of the bar. 70s, less than half. 80s, female income little less than half, right? Check out 1990. Looks like, I'm not measuring exactly, but it looks like female incomes reached about half of that of males in the 90s. And then if you follow the trend or follow the multiple bar graphs, it looks like there was a trend where the female incomes, it's kind of gaining. Half point might have been right here. So females passed up the half point. And then even here, it looks like passed up even a little more so. So you can see, hopefully, you can see that if we were just presented with a bunch of incomes, just numbers, it would be very challenging to find a trend or to compare groups. But when we use a table or a graph, it helps, those visual tools help us identify those things. Pareto chart, same thing. It's got percentages on its horizontal axis, but this time we're talking categories. So Pareto chart would be used for categorical data. Like this one is what contributes most to happiness. So category options, family and partner got the most. It actually got looks like 65% of people surveyed said that family/partner contributes most to happiness. Then there was a big decrease, but the next highest was friends, then leisure, then work study, then music, then sports. So with this Pareto chart, you can quickly identify categories, percentages, and as they decrease, how quickly they decrease might show like, wow, this one is very important. Maybe it decreases a little slower and you would have a different type of conversation about what contributes most to happiness. The pie chart, believe it or not, this is exactly, this is the same data as the Pareto chart. It's just put into a circle. So instead of bars, we have sectors or wedges of the circle. And instead of heights, we've got the arc length here. So this is the smallest wedge. This area is the smallest, so that the least amount of people said sports. Then more for music, more for leisure, more for work studies, more for friends, and then the most we can see here for family partner. Both were good visual tools to show that family/partner had more than half of the people identify that category as what contributes most to happiness. So you guys, it's important that you recognize that both of these have to do with percentages, okay? At no time did we say how many people said family versus partner. So Pareto charts and pie charts are about percentages of the whole, which is why a lot of people do pie charts. It's a whole circle. So this would be the percentage. Same thing here, this percentage on the vertical axis. Graphs that deceive, a non-zero axis. Graphs can be misleading because one or both of the axes begin at some value other than 0, so the differences are exaggerated. All right, if you were to go on social media and you were looking to buy a car and you saw this graph right here, and you're comparing, okay, I need a car with good miles per gallon because gas is expensive, or that's important to you. You're comparing the Honda Civic to this Chevy to this Toyota here, and you see this graph. It is meant to deceive you. It is not starting at 0. What that means is that it's like you're zooming in on the tops of the bars, and the difference is exaggerated, okay? Notice, let me try again. Check out the Toyota Camry. This distance right here, if you go then and compare that to the Honda Civic, that's 1, maybe 2 right there. Let me mark them off with tick marks. I'm going to try to draw that same length here. That's 3. Try to draw that same length again, like that, maybe 4. So by exaggerating these differences, it looks like the Honda Civic gets about 5 times as many miles per gallon as the Toyota Camry at quick glance. And a lot of us, as we're scrolling through social media, quick glance, that's what we do, right? So it's important. And one of the main reasons we study statistics is so that we don't glance too quickly. And if we do, we know what to look for. You want to look for graphs that start with the axis at 0, and if they don't, you need to go, okay, even though this isn't inaccurate, it is exaggerating the differences visually using this visual tool. This one here where the axis starts at 0, it's the same data. It looks different, and it shouldn't. No matter which graphing tool you use, the consumer or person you're presenting to should get the same feeling from it, unless you're trying to deceive them in some way. So here, looking at the heights of the bars, the Toyota Camry, try to draw the same height right there. So the Civic looks like it gets more, but definitely not 5 times as many miles per gallon. It's called the non-zero axis. Same thing happens with 2-dimensional and 3-dimensional shapes. For example, here, when we're talking dollars, that's linear data, okay? This is income and education. Bachelor's degree, you get 51,206. Maybe this was an annual salary for a certain year of those who have obtained a bachelor's degree. Advanced degree, 74,602. Okay, so this is the data, these dollar values here. But up here, we have this visual tool that they're attempting to use. But the visual tool that they're using is a 3-dimensional tool. 3-dimensional tools should not be used to represent dollars, which are first-dimensional. Reason why, the volume of this little cube right here, okay, let's say it's a 1 by 1. So its volume would be 1 cubic centimeter if it were a 1 by 1 by 1 cube. 1 cubic centimeter. Let's say this one were a 2 by 2 by 2. here a 3 by 3 by 3, and here a 4 by 4 by 4. The 4 by 4 by 4 would have a volume of 64 cubic centimeters. So the visual, three-dimensional representation of the data is showing that this is, you go from 1 to 64 times as much. But if you look here at the numbers, the actual data, not the visual tools, 18,000 to 74,000, that is not 64 times as much. So using a three-dimensional tool is misleading. So make sure next time you're scrolling through social media or watching the news or see a billboard, if you can find any of these deceiving techniques, point it out and start to think about those and use that information to help you make decisions in your life about, well, what type of car to buy, jobs and related to school, and every other topic you can find some valid data for. All right, that will finish our discussion and video for Chapter 2. My name is Jamie Amy, and I will see you all next time.